Okay, so Noel and Kelvin, we meet again. So I hope you both are not confused lah, because I am the third lecturer who teach this course. Because of some MQA arrangement, some MQA rules we need to follow. So that's why we need to do this arrangement. Okay, so if according to our course plan, which is course plan lah from B, in week 9, which is this week, we will continue the lecture in algorithm for searching and algorithm for sorting. So algorithm for searching is your chapter 7, and I was informed by Mr. Jeffter that he already covered this chapter 7, and then algorithm for sorting also he already covered up until selection last week. Okay, so for this week we should continue with insertion, algorithm for sorting for insertion. Okay, am I right, Noel? Last week.
Iya.
Okay, so next week we will still in algorithm for sorting. And for this week, we only so Mr. Jeffter covered up until selection, and then now we proceed to insertion. But for the exercises, for example, this one, we will cover next week. Okay, because the material I received previously was corrupted, so I only get the PDF version. So that's why I don't really have enough time to test all of the exercises. So we will cover that next week lah. For this week, it is more on understanding the sorting algorithm for insertion, quick sort, and merge sort. Okay, so this chapter at B is about bubble sort, selection sort, insertion sort, merge sort, and quick sort. But Mr. Jeffter already covered these two algorithm, then we proceed to this three lah. And then okay, so wait, let me okay. So even this PowerPoint also I just get this morning lah. Okay, so I previously I only have the PDF, but now we already have the PowerPoint. I believe Mr. Jeffter also teach you all using the PDF version, but that is actually because he also got the corrupted files. So all of the PowerPoint cannot be opened. Okay,
Iya.
that's fine. Yeah, I saw his video. He is using the PDF. Okay, but yeah, so now you all know lah where we are right now. Okay, so now we will proceed insertion, merge, and quicksort. Okay, so and then we will assess big O notation for each of these sorting algorithm lah. Okay, so we skip this. Okay, so insertion. This insertion sort, actually, if you read all of this, it's hard to imagine. Okay, so I found a very good YouTuber, actually. I'm not sure if maybe any of you already discover this guy, Michael Sembol. So he is very good explaining. Oh no, okay, good. Like that. So I am giving you new information lah, if like that. So if you see here, he is someone that covered DSA, and his explanation is if you see here the view, all of his videos is getting about thousands views lah. Okay, so usually for the educational video, usually it won't get this high lah if it is not really good. So I suggest you both to check and subscribe his channel, and then you can see, you can watch later the bubble sort, the selection sort. But now because we are proceeding to the insertion, then we go to see the insertion. Okay, so you see here, it is all of his video, only about few minutes, 2 minutes, 3 minutes, up until 5 minutes. Okay, so all of it, the longest minutes is only 5 minutes. And he actually summarize and visualize whatever we have in our slide. Okay, so if you read this partition, this strategy or this algorithm, this insertion algorithm, it will partition the array into two regions, and then which is the first region is sorted, and then the second region is the unsorted, and then the algorithm will take each item from the unsorted region and insert it into its correct order in the sorted region. Okay, so this is very theoretical. So we see the video, it will help you all understand, actually visualize whatever happened or whatever described in this slide. Okay, so we see first, insertion in 2 minutes only. I share we watch together. Already passed the
Today we're going to learn
link in our chat.
Okay.
So we watch together.
Today we're going to learn insertion sort. Let's dive right in. We're given this array and we want it sorted in increasing order. Here's what we're going to do. We'll start at the left and work our way to the right, examining each item and comparing it to the items on its left. We'll then insert it in the correct position in the array. You'll notice that part of our array will be sorted as we progress. We'll mark those items with a green background. Let's begin and you'll see what I mean. We start at 2. Of course, there are no items to the left of 2, so we mark it as sorted. Moving on to 8, we compare it to 2 and leave it where it is. Our first 2 items are now sorted. Next we have 5, which we can see is out of place. We know it needs to be after 2, so we swap it with 8. Our first 3 items are now sorted. On to 3. Again, it's out of place. We swap it with 8 and 5 until it's in the correct position. We're at our 5th item, 9, and I'm sure you can see that it's in the correct spot. Let's move to 4 and insert it in the correct place in the array. And that's it, we're done. Insertion sort is one of the most straightforward sorting algorithms. For your reference, here's the pseudocode. Insertion sort has the worst case time complexity of big O of n squared, where n is the size of the array. For example, when an array starts in decreasing order, you need to swap and compare every single item, which leads to big O of n squared. Thank you for watching. I'd love it if you subscribe. Please post suggestions for future videos below.
Okay.
Okay, done, right? Okay, so maybe if you just watch it for the first time, you may need to repeat it again later. Okay, so you can subscribe his channel and then find a lot of video lah from his channel. Okay, so whatever actually he just visualized just now is actually what described here. So how does it work? Okay, so make n negative, not negative, sorry, n minus 1, this is referring to the position of the array, passes through a sequence of n elements. Okay, so okay, so I want read this again because you all can visualize how this algorithm works already by watching the previous video lah. Okay, so but the most important thing, this insertion sort, it is faster than bubble and selection sort that you have previously learned. Okay, so because why? The elements in the array is shifted. Okay, so and then there are no swapping of the elements. Okay, so this is the another explanations or analogy of how the insertion sort works lah. So if, for example, this is the first partition, which is the sorted partition. Wait, so if first two books are out of order, okay, these first two books out of order, we remove second book and then slide first book to the right. Okay, so for example, so if you remember previously in the video, it works from the left to the right. Okay, so if I think you can ignore this if because the video is better because it use the numbers. For this, it use the size or the height, the head of the books. Okay, so just ignore this actually because it is already explained in the video. Okay, so this is actually what happened in the in our video just now. So there are two partitions, which is sorted and unsorted. So it assume the first element in the array is the sorted one, and then for the first iteration, it is called as a pass 1, pass 2, pass 3, pass 4, pass 5. It is actually iteration. So the first element will be in the first partition, which is the sorted partition, and then the rest will be in the second partition, which is unsorted. So after that, for the first iteration, it will compare the element in the sorted partition with the element in the first unsorted partition. So it will compare. This the first element with the second element in the unsorted partition, and then it will insert this 45 into this position. Okay, because it is works from left to the right and then in increasing order. Okay, so After that, it will compare the all of the unsorted. The process will be continue until the largest will be at the end of the array. Okay, so this is actually whatever explained in our video just now. We watch it again now. Each of these, it will compare with this in the sorted array, and then in the sorted partition. Each of the first element in the unsorted partition, it will compare with the element in the sorted partition. And then, if for example here, add, it compare with the 78, and then it found that this add is smallest than 78, and then it will move this and then put add here, and then after that add will be compared with the 45, and then because add is smaller than 45, then it will take the 45 position, and then after that the add will be compared with the last element in the sorted partition, which is 23, and then it will replace the 23 since add is the smallest. Okay, so this process will repeating until the largest will be at the end of the array, and then the smallest in the the smallest will be to at the most left of the array. Okay, so I know that you both already learned about it. What is the iterative algorithm and recursive algorithm? Okay, so this is the iterative algorithm for this insertion. All of this concept, it is transformed in this iterative algorithm using code. Okay, so it used two functions, which is first insertion sort, and then another in the function is insert in order. Okay, so these functions will use this function. Okay, so this function will receive three parameters, which is the elements, and then the A is the array. Okay, so the N is the total number of element in the array. Okay, so this can be called, this is the iterative algorithm lah. Okay, so for the recursive, I think I won't repeat again what is iterative algorithm and recursive algorithm lah, because it is already covered. And then, but in short, recursive algorithm is the algorithm that call its own. It is algorithm that call its own function, or the algorithm that call itself. Okay, the example here, recursive algorithm. Sorry, so in this insertion, it didn't show what is the recursive algorithm, but this is the example of recursive algorithm for the selection sort. So if you see here, the recursive algorithm is the algorithm that calling itself. For example, here, this is the function selection sort, but in its step or in the algorithm in this function, it is calling itself. Okay, so this is recursive algorithm in short. So I know that recursive algorithm, there are a lot of explanation about it, and you already cover it. And then, but in short, recursive algorithm is select the function that call itself lah. this one. For the iterative, it is the iteration. It doing the iteration. Okay, without calling itself. Do you all understand about the iterative and recursive algorithm previously?
Yeah.
Yeah, easier for me to apalah. Okay, so we watch again that video. We watch again. You'll click
Today we're
the
going to learn insertion sort.
YouTube.
Let's dive right in. We're given this array and we want it sorted in increasing order. Here's what we're going to do. We'll start at the left and work our way to the right, examining each item and comparing it to the items on its left. We'll then insert it in the correct position in the array. You'll notice that part of our array will be sorted as we progress. We'll mark those items with a green background. Let's begin and you'll see what I mean. We start at 2. Of course, there are no items to the left of 2, so we mark it as sorted. Moving on to 8, we compare it to 2 and leave it where it is. Our first 2 items are now sorted. Next we have 5, which we can see is out of place. We know it needs to be after 2, so we swap it with 8. Our first 3 items are now sorted. On to 3. Again, it's out of place. We swap it with 8 and 5 until it's in the correct position. We're at our 5th item, 9, and I'm sure you can see that it's in the correct spot. Let's move to 4 and insert it in the correct place in the array. And that's it, we're done. Insertion sort is one of the most straightforward sorting algorithms. For your reference, here's the pseudocode. Insertion sort has the worst case time complexity of big O of n squared, where n is the size of the array. For example, when an array starts in decreasing order, you need to swap and compare every single item, which leads to big O of n squared. Thank
you. You both understand more which explanation from this slide, meaning this book analogy or the one in the YouTube?
The YouTube.
Okay, so for me, if I read this, I also will, I know that each of these, it will compare the height of the book and then it will swap lah, which is from the paling pendek to the paling tinggi, from the shortest to the highest book. So that is the summary lah of this. Okay, so if you don't understand this, then you can understand it more from the YouTube lah. Okay, so in this algorithm for the recursive for insertion, it only tell how it will be done, but it didn't tell the code exactly. Okay, so because later they will ask you to do the recursive algorithm lah, so that's why. Okay, so we proceed with this first because in practical ed, if I'm not mistaken, you will do this recursive algorithm. Okay, so efficiency for insertion sort, and then from your previous lecture, I saw that there's the lecture about this efficiency of algorithm, which is the big O notations. So you know, in conclusion, what I can see what I can say, what I can say about the big O notations, the best algorithm is the algorithm that has big this I forgot how to pronounce this. Who remember how to pronounce this? Big O N.
Big big O of n.
Pardon?
Big O of n.
Big O of N. So this one, big O of.
N square.
Okay, so I know that in conclusion, for the efficiency of an algorithm, the best is this big O of N, and then the worst is big O of N square. Okay, so it says that this insertion sort algorithm can have also this the best efficiency lah, which is this, and then it also can have this worst time efficiency, which is big O n square. Okay, so if I also have found from the same person, this one, big O notation introduction in 5 minutes. As a refresh, sorry, this is it is the big O in 5 minutes. This one. This guy also have provided video about big O notation, so you can watch this.
Is it? Today we're going to learn about big O
Even though you
notation.
already learned about the big O notation, but maybe this video will help you more lah, because it visualize it better lah, all of the theory. Okay, so we watch that together lah.
So what is it? Big O notation is simplified analysis of an algorithm's efficiency. We cover a lot of algorithms on this channel, and we need a way to compare them and some idea of how long they'll take to run. Big O gives us an algorithm's complexity in terms of the input size, n. It gives us a way to abstract the efficiency of our algorithms, or code, from the machines they run on. We don't care about the stats of the machine, rather we examine the basic computer steps of the code. We can use Big O to analyze both time and space. There are a couple ways to look at an algorithm's efficiency. We can examine worst case, best case, and average case. When we're talking Big O notation, we typically look at worst case. This isn't to say the others are unimportant, however. Let's talk about a few rules. First, Big O notation ignores constants. For example, if you have a function that has a running time of 5n, we say that it runs on the order of Big O of n. This is because as n gets large, the 5 no longer matters. In the same way, as n grows, certain terms dominate others. Here's a list, but I'll show you a visual on the next page. We ignore or drop low-order terms when they're dominated by high-order ones. Take a minute and study this chart. It can be found on bigocheatsheet.com, along with a handy guide on the Big O of various important algorithms. Let's run a few examples so you can see what I mean by basic computer steps. We'll start with constant time. Imagine we have the following line of code. This basic computer statement computes x, and notice, it does not depend on the input size in any way. We say this is Big O of 1, or constant time. What happens when we have a sequence of statements? Notice that all these are constant time. How do we compute Big O for this block of code? We simply add each of their times, and we get 3 multiplied by Big O of 1. But remember, we drop constants, so it's still Big O of 1. Let's look at linear time. Suppose we have the following for loop that prints the numbers 0 to n. We know the print statement is big O of 1. This means the block of code is n times big O of 1, in other words, big O of n. Here's another sequence. The first line we know, again, is big O of 1, and the for loop is big O of n. The total time is the summation of these two, but remember we drop low order terms. When n gets large, the time it takes to compute y is meaningless, as the for loop dominates the runtime. Finally, let's look at quadratic time. I think you can see that the print statement will be executed n times n, which gives us big O of n squared. Let's do two more examples covering everything we've talked about. Say we have the following block of code. What is its total runtime? Well, we know the runtime for each of these, so the total runtime is simply the max of the three. The nested for loop dominates here, so we get big O of n squared. How about this if-else statement? Pretend the sequence of statements in each clause have already been deduced to the big O's shown. We talked earlier that when we're discussing big O, we usually look at worst case scenario. So for this situation, we choose the largest runtime, which happens to be big O of n squared. I hope this gives you an understanding of big O notation. Let's wrap up by talking about the real world. When you're coding your algorithm, please realize that constants absolutely do matter. A lot of situations have small input sizes, so a constant of 2 or 3 could have a large impact. Lastly, for the same reason, be cognizant of best and average case. Depending on your application, this may be more applicable for your algorithm. As always, thank you for watching. Please subscribe if this helped you.
Okay, so from the summary, to conclude about this video, we know that based on the complexity chart here, this one, the operation, if it is involved this big O of n, it is actually faster than this. And then the operations or your code that involve n square is the worst. Okay, so the fastest one, the efficiency of running your code is the operations that involving this big O of 1 or a constant. Okay, so from this video also, it shows the example of an operations that considered as big O of n square. Okay, so for example, this one is the big O of 1, which is the fastest time, I mean the fastest algorithm. If you write this kind of algorithm, it can be processed fastest among, I mean, if it is compared with another algorithm. So this will be the big O of n, which is there are actually big O of 1 here, but it is for x time. So meaning it is big O of n, meaning there's constant code that is run for X time. So that is under big O of N category. So this is big O of N. This is example of code that will be under big O of N, meaning we categorize its effectiveness as big O of N. So if you have nested loop, this is the example of how we get the big O if they are two types of operations. For example, here there's a constant and there's a big O of N. So we take the worst, which is if compared with this, there are two, right? So for this operation, we take the worst, which is big O of N. Okay, so we will eliminate the constant. Okay, so after that, for the quadratic time or nested loops, here if you see, you have these constants actually, but it will need to be looped 2 times. It will be in the nested loop, which is it will be looped 2 times lah. Okay, so if you find or if you code this type of algorithm, that means your algorithm have big O of n square if yeah, big O of n square lah. Okay, so this type of algorithm will take more time compared to the previous algorithm. Previous big O. Okay, so for example, this one, like previously, it will take the worst. So we have 3 types of big O in this code, which is the first is the big O of constant, which is big O of 1. And then this is the big O of n, and then the big O of n squared. So as the previous notes or the previous example, we will take the worst. Okay, so for this code, it will be big O of n squared. Okay, so this is the big O value, big O for these questions, this code. So what if we have if else? And then in each of the if else, it has different big O. So as usual, it also will take the worst, which is big O of n squared. Okay, so this type of code also will fall under category of big O n squared because the worst big O here is the big O n squared. But in practice, actually, we cannot ignore constants because processing constants also will contribute time in processing times of your code. Okay, so, and then be cognizant. Be cognizant is actually be aware of best case and average case also. So we don't only focus on the worst case, but you also need to be aware about the best case and the average case. Okay, so this is actually, I think, summarizing the chapter 3. Okay, but I hope that video will is not making you more confused lah about what you have learned in chapter 3. Because do you more understand about this video or makes you confused?
Yeah, I prefer this one better.
Yeah, good lah. Okay, so Kelvin also lah, right? So I hope you really subscribe this guy lah, because he really, you go to the video, he really explain better lah in short time. Okay, so in short, the efficiency of insertion sort is it can also achieve big O of n, and it also can achieve big O of n squared. Okay, so but this insertion sort is more suitable for the small array size, because the algorithm process, if it is involve a big array, it will take time. Okay, so all of the algorithm previously that we have learned, insertion, selection, bubble, those three memang suitable for small array size. Okay, so this one, like I said, we will cover this next week. To do this exercise. But now we proceed to the quicksort, and then after this we will proceed to the merge sort. Okay, so this quicksort also it also divide the array into two segments. It is previously in the insertion, it also divide the array into two partitions, and then here also it divide the array into two segments. But the difference here in quicksort, it has pivot value. Okay, and then this quicksort algorithm also is actually a recursive algorithm. And then the two segments is left and right. In the previous, it is called as sorted and unsorted. But for this one, it is left and right lah. And then there will be a pivot value. So what is pivot value? We will see later. Okay, so this quicksort use pivot element and rearrange the array elements. Okay, so the pivot is in its final position in sorted array. Okay, so it will stop the arrangement after the pivot value is in its final position in that sorted array. Okay, so elements in positions before pivot are less than the pivot. So whatever elements in the left is will has the value that is less than the pivot value. Okay, so after that, the element after the pivot will have the greater value than the pivot value. So we will see later what is the pivot lah. So this arrangement is called a partition of an array. So this quicksort will usually fast in practice. So even in the worst case occur, the quicksort performance is acceptable for moderately large arrays. Okay, so the first three algorithm is suitable for small array size, but for this quicksort, it is acceptable for moderately large arrays now. Okay, so we see here the pivot value. The algorithm will pick one value inside the array element and then make it as a pivot. But we see later how they will choose the pivot lah, the value. And then in the left of the pivot value, all of the value will be smaller than the pivot value. And then in the right element, the the value will be larger than the pivot value. So we will see better in this video also, which is pivot. Quicksort. Okay, so the link in our
Today we're going to learn Quicksort. Like mergesort, Quicksort is a recursive algorithm. However, when you think of Quicksort, I want you to think of the word pivot. A pivot is simply one of the items in the array that meets the following three conditions after we've sorted it. First, the pivot is in its correct position in the final sorted array. This means that all items to the left are smaller and all items to the right are larger. Let's look at an example. We're asked to sort the following array. Let's choose a pivot. I'll explain the best way to do this later, but for now let's just choose 3. First, we move the pivot to the end of the array to get it out of our way. Next, we're going to look for 2 items. Item from left, which is the first item starting from the left that is larger than our pivot. Second, item from right, which is the first item starting from the right that is smaller than our pivot. Starting at 2, we can see that 6 is item from left. Now starting at the right, we see that 1 is item from right. Let's swap item from left with item from right. We repeat the process. This time, 5 is item from left and 0 is item from right. Again, we swap the 2. One more time. This time we see that item from left has a greater index than item from right, so we know we're done. We swap item from left with our pivot. Three, our pivot, is now in its correct spot. To prove it, let's review our 3 conditions. As you can see, all items to the left are smaller, and all items to the right are larger. We said Quicksort is recursive. Let's go through the process one more time with the larger partition we just made. We'll choose 7 as our pivot and move it to the end. I'll let you watch without voiceover. Now we have 3 and 7 in their correct positions. I think you understand the concept, so we'll let recursion handle the rest. One important question is, how do we choose the pivot? This makes a large difference in the performance of the algorithm, as we want to choose a pivot that divides the array in half, or as close as possible, to even out the work. One popular method is called median of 3. In this method, we look at the first, middle, and last elements of the array. We sort them properly and choose the middle item as our pivot. We're making the guess that the middle of these 3 items could be close to the median of the entire array, and as you can see, it's not too far off. Here's the pseudocode for Quicksort. Quicksort has the worst case time complexity of big O of n squared. But if a pivot is chosen properly, it can be shown to have an average case of big O of n log n. Thank you for watching. Please like and subscribe if you enjoyed the video.
We watch again because I know it will be a little bit slower to digest if you just watch it for one time. So let's watch it for the second time.
Today we're going to learn Quicksort. Like mergesort, Quicksort is a recursive algorithm. However, when you think of Quicksort, I want you to think of the word pivot. A pivot is simply one of the items in the array that meets the following three conditions after we've sorted it. First, the pivot is in its correct position in the final sorted array. This means that all items to the left are smaller and all items to the right are larger. Let's look at an example. We're asked to sort the following array. Let's choose a pivot. I'll explain the best way to do this later, but for now let's just choose 3. First, we move the pivot to the end of the array to get it out of our way. Next, we're going to look for 2 items. Item from left, which is the first item starting from the left that is larger than our pivot. Second, item from right, which is the first item starting from the right that is smaller than our pivot. Starting at 2, we can see that 6 is item from left. Now starting at the right, we see that 1 is item from right. Let's swap item from left with item from right. We repeat the process. This time, 5 is item from left and 0 is item from right. Again, we swap the 2. One more time. This time we see that item from left has a greater index than item from right, so we know we're done. We swap item from left with our pivot. Three, our pivot, is now in its correct spot. To prove it, let's review our 3 conditions. As you can see, all items to the left are smaller, and all items to the right are larger. We said Quicksort is recursive. Let's go through the process one more time with the larger partition we just made. We'll choose 7 as our pivot and move it to the end. I'll let you watch without voiceover. Now we have 3 and 7 in their correct positions. I think you understand the concept, so we'll let recursion handle the rest. One important question is, how do we choose the pivot? This makes a large difference in the performance of the algorithm, as we want to choose a pivot that divides the array in half, or as close as possible, to even out the work. One popular method is called median of 3. In this method, we look at the first, middle, and last elements of the array. We sort them properly and choose the middle item as our pivot. We're making the guess that the middle of these 3 items could be close to the median of the entire array, and as you can see, it's not too far off. Here's the pseudocode for Quicksort. Quicksort has the worst case time complexity of big O of n squared. But if a pivot is chosen properly, it can be shown to have an average case of big O of n log n. Thank you for watching. Please like and subscribe if you enjoyed the video.
Okay, so Dan watch for the second time.
Yeah.
Can understand or grab the concept?
Yeah.
Kelvin? Still a bit confused. Yeah, so later you can rewatch that again lah. But my highlight here, to choose a pivot, you already know how to choose the pivot. It is using the median of 3 concept. First, if we have this unsorted array, we just tag the first, in the middle elements and the last element. And then after that, we sort this element based on the increasing way. So we swap 4 in the middle and then add in the end because it is increasing. 2, 4, and add. Only focus on these 3 elements, which is the first, the middle, and then the end. Okay, so after that, we sort that value. And then after that, we take the middle after we sort. Okay, so from this array, we can choose the pivot, the guy call it pivot. The pivot is 4. So understand how to choose this pivot? Only for this part lah.
What if number number and array? It's not odd number. Even number, how to choose the middle one?
So you better 1, 2, 3, 4, 5, 6, 7, 8, 9. Usually, you can choose either. For example, if there are, this one is 9, of course there will be the middle value, right? But if it is 8, then you can take either the item number. For example, we don't have 8 here, so we only have this 8. So 1, 2, 3, 4, 5, 6, 7, 8. So you can take either the 4th elements or the 5th elements. Okay, either 2 lah, because we don't have the real in the middle value, right? So we can take either the 2 value in the middle lah. Okay, Kelvin?
Okay.
Okay, so that is how to choose the pivot. And then I think another things that we need to understand is how to stop, how to make the process here stop, and then we put back the pivot value in the array after we move it in to the end. Okay, so there are a formula here. Okay, so here we stop swapping item from right and item from left after the index of item from left larger than index of item from right. Okay, so after this swap, we know that this item from left larger than item from the right. So if this condition is met, we move back this pivot number between the item from the right and then the item from the left. Okay. We move it after we meet the condition, we swap the item from the left and the pivot. So we swap this with the pivot. Okay, so after that, now we have 2 partitions. After that, the algorithm will take only the upper partition or the right partition and then repeat the process as previously. And then after it done, and then it will do the partition on the left. Okay, so remember there are few formula here. Like I said, the swapping will stop when the index of the item from left larger than index of the item from the right. And then after that, when that condition is met, we move the pivot, we swap the pivot value with the item from the left. After that, we have 2 partitions where all of the value from the right is actually larger than the pivot value. And then all of the value from the left is smaller than the pivot value. So when this condition met, the algorithm will take the items from the right, which is all larger than pivot, and then do the algorithm again, swapping it again, meaning choosing pivot and then compare it, and then after the condition met just now, and then it will put back the pivot value and then swap it with the item from the left. Okay, so that process will continue for this part, and then it will also continue the process from this part. Okay, so maybe Kelvin or maybe Noel, if you still confused, maybe you can rewatch that video again later in the smaller, in the quieter place when there are no voice from me, where I didn't speak. Okay, sorry, somebody is coming in. Okay, so that is the Quicksort. So I hope you can grab the concept. And then actually it is not easy to transform this concept. But if we can grab the concept logically, the logic of that concept, then we can we can understand more on how to do the algorithm lah. So this is the algorithm for the quicksort. You need an A first and last. Okay, so first we sort the array elements. This is the array. And then after that, as long as the first element is still smaller than the last element, we still can choose a pivot. And then partition the array based on the pivot. And then we take the pivot index, meaning pivot index here is the position, the address of the array. Okay. Okay, so after that we do the quicksort. So remember this quicksort memang implement the recursive algorithm where it is calling itself. Okay, so this is quicksort. It is also calling itself. So this is this is why it says that quick algorithm is a recursive algorithm, because it is calling itself here. Okay, so follow this algorithm lah for the quicksort. So like in the video just now, the worst case of this quicksort is big O of n square, and then in the average case, the efficiency can achieve this big O of n log n. Okay, so this worst case can be avoided by careful choice of the pivot. Okay, so we can avoid this when we choosing the pivot carefully. Okay, so how? By following the median of 3 formula just now lah. Okay, so that is actually one of the way of choosing the pivot. So there are more technique, but the one that is commonly used is the median of 3 just now lah, like what described in the video. Okay, so some pivot selection schemes can lead to worst case behavior if the array is already sorted or nearly sorted. So this quicksort, faster than merge sort, it also doesn't require the additional memory that merge sort needs for merging lah. So later we will see how the merge sort works. So this is actually whatever in the video just now. We can just skip this. Okay, so Quicksort rearrange the elements in an array during the partitioning process. Okay, so after each step in the process, one element, which is the pivot, is placed in its correct sorted position. So this is the process where the condition just now is met. This is what it means. Okay, so when this condition, the swapping will stop when the item from the left, the index of the item from the left is larger than the index of the item from the right. So one element, one element, which is the pivot, is placed in its correct sorted position after that condition is met. Okay, so the elements in each of the two subarray will remain in their respective subarray. So the subarray here referring to the subarray that is in the large partition and then the subarray in the small partition. This is the subarray. Oh, wait, sorry, I was distracted. Okay, so this is the partition of the subarray, which is the larger partition, and then this is the small partition. So each of the elements in its partition will remain in its partition. It will not go to another subarray. Once we already place the pivot in its place, and then it will divide the array into two subarray, which is the large and the small. And then each of the element in the subarray will not mix again. Okay, so this sort method is implemented in these functions in our Java util. Okay, so the example of implementation of Quicksort is actually, do you already have the sample code? Is it already uploaded in our Google Classroom?
Where?
The sample code. In the sample code, kan?
Oh, I'm checking. The sort array.java.
Pardon?
Oh, I think already in the GC.
In the GC, in
Right.
week what?
Week 8.
Yes, this sort array. Okay, so you can see the implementation of this sort array, this Quicksort in this class, in this ADT, abstract data, ADT, abstract data type. Sorry, so I open my NetBeans. Can you all open do you have any problem using NetBeans? No?
So far, no. Miss, this is 8-bin version 13.
Yeah.
Oh,
My version is 13, the latest.
oh, okay.
So if you see the implementation of the Quicksort, if you see here, there are there are 3 methods. Okay, there are 3 methods that will help in implementing the Quicksort. So appendix, this one is visualizing. Appendix at point 1 is the visualizing. Wait, I need to see either in our Google Classroom, there are appendix 1 at point 1. So this is actually the visualization of Quicksort in diagram. So you can see this letter. Let me check in our Google Classroom if it is already uploaded. So I think no, I will upload now. Because this material also I just got just now, this appendix at point 1. I'll create topic first. Week at plan. Appendix at point 1. Yeah, so I already uploaded this appendix at point 1. So you can refer later for the Quicksort. It visualized whatever in the video just now, but it is in the diagram. So we proceed with the merge. This one is the pivot selection. So this is actually whatever in the video just now, which is we choosing the pivot value based on the median of 3. Okay, so this is the theory part of it. So first we choose the median, I mean the first, and then in the middle, and then in the last position elements of an array. And then after that, we sort it. We sort the 3 elements in the increasing way. And then we choose the middle value after it is sorted. Okay, so this is what in the slide just now, not slide, video. Okay, so so this is also how to swap. Okay, so this is after we choose the pivot, we move it in the end. And then after that, we check the index from the left that is larger than the pivot value. So which is at, and then we choose the index from the right, the value from the right, which is, for this one, it may be different a little bit from the video because this is not smaller than the pivot value. It is because from the previous video, it says that we take the index from the right, which has smaller value than the pivot value, right? But this one is not the but the array with its first, middle, and last element sorted, and then the array after the positioning the pivot and just before the partitioning. This way is a little bit different from the in the video because it will not positioning the pivot at the end of the array, but it will position it at the second last because it already after it arranged, the 9 is the largest, I think. That's why it put the pivot value not at the end, but at the second place. But as in the video said, that there are a lot of way of choosing the pivot. So in the video, the algorithm is putting the pivot value at the end of the elements of the array. But our slide said it needs to be put at the second last element. But for this one, I will double confirm with you all next week. Okay? Because I want to sure where is better lah, either from our video or this from our slide.
Okay.
But you see the difference lah, right, Noel? Can you see the difference?
Yeah. Maybe,
Because
yeah.
Because if you see the pivot value after we identify the pivot value, it is put in the second place. But in the video, median of 3, it also used the median of 3. And then you see after it choose the pivot, then it do the swapping. But in this example, it moved the pivot to the end. So I will explain this next week. Quicksort, how to choose pivot slide. Okay, so in order for comparing all of the we proceed with the how to do the comparing when we do the quicksort. Okay, so we use the comparator interface. Wait. Sorry, somebody wants to go in the room, so yeah. Okay, so in order to do the quicksort algorithm, we need to use the comparator interface. Okay, so for comparing objects according to an order other than their natural ordering. Okay, so we use this comparator interface to compare the object according to an order that is other than their natural ordering. Okay, so a comparator is an object that is external to the class of the keys it compares. So it provides multiple or alternative sorting sequence. For example, you can compare elements based on any data member. So, for example, if the natural ordering is based on alphabet F from Z, but using this comparator interface, we can compare any element that is not following the natural ordering. For example, the alphabet following the alphabet order or following number in decreasing or increasing way. Okay, so using this comparator, we can compare two elements that is not following natural order. For example, we compare object 1 and object 2. Okay, so we return the integer with similar meaning to the compare to methods of the comparable interface. So in the comparator interface, we have one method which is compare. So this compare can compare between two objects. So another class that we need to use in order to implement the quicksort algorithm is the collection class. Okay, so this collection class provides static methods for sorting the elements of collection. Okay, so this collection class, it has methods that can sort. This sort is the static method. Okay, so this sort can be used to sort the elements in any collection. For example, list. Okay, so we have list object, and then we have a comparator object from this comparator is interface. You both have already learned about the interface, what is interface, what is a regular class, right? So I don't need to explain this.
Oh yeah.
So this comparator is interface, and then this is a regular object class, which is list. So we have we need this sort will need to receive parameter, which is first from collections, and then the second parameter is from the interface. So this sort method is used to sort the elements of list by given comparator. Okay, so this sort method, it is from collection interface, and then this method is a static method and it receives two parameters. Okay, so the sort method is used to sort the elements of list by given the comparator. Okay, so if we want to sort the array of the type of list, then we can use this sort. So this sort implementing Quicksort algorithm. Whatever that we have learned previously, it is implementing the Quicksort algorithm. So we will test this code next week. We already have the code and then we will test this. This is implementing the Quicksort. Okay, so but next week we will cover this. So now we proceed to the merge sort. We have about 30 minutes to cover this. So this merge sort is another recursive algorithm, which is it is calling itself. The algorithm will call itself, the function itself. Okay, so it gives the same performance with the Quicksort, regardless of the initial order of the array item. And then the strategy of this merge sort algorithm is it will divide the array into two halves. And then it will sort each of the half. Okay, so after that, it merged the sort halves into one sorted array. So that's why this algorithm also called as divide and conquer algorithm, because first it divide into two, and then after that it merge again. Okay, so after it divide into two half, it will sort each of the division or each of the half, and then after that, after it sort and then it merge again. So that is the merge sort. But if you remember just now, Quicksort is faster than merge sort. Okay, so I think rather than looking at this diagram, we better go to our video from Michael Sambol, and then we search for merge sort. Okay, the video is in our chat.
Today we're going to learn merge sort. A few quick points, then we'll get to the example. Merge sort is usually done recursively. When you think of merge sort, as with other recursive algorithms, I want you to think of divide and conquer. We're going to break our problem into smaller problems in order to solve it. Let's get started. We have the following array and we want it sorted. We're going to continuously split the array in half, our divide step, until we are left with the individual items. Watch and see. Our array is now broken down into individual items. One note before we start sorting. When you implement this in code, these steps will be done in a different order because of recursion. But I think this human-friendly order provides more clarity in learning. Let's continue. We're ready to sort. We'll examine the individual items, compare their values, and merge them into temporary arrays. The temporary arrays are sorted, but there's work left to do. Let's jump up the recursion stack and continue. We merge our smaller arrays into a larger one, inserting items in the correct order. One more merge, and we'll have our sorted array. And that's it. Our array is now sorted. Here's the pseudocode for merge sort. On the left you have the recursive part, which halves the arrays. On the right is the merge function, which combines the arrays. Merge sort has a worst case time complexity of big O of n times log n. The easiest way to think about it is to start with the merge step. Looking at the while loop, we see we have to visit n items. The log n comes from the maximum height of a binary tree we create, which is on the order of log n. Thank you for watching. Please comment suggestions for future videos below, as well as any questions you may have.
Watch again.
Merge sort. A few quick points, then we'll get to the example. Merge sort is usually done recursively. When you think of merge sort, as with other recursive algorithms, I want you to think of divide and conquer. We're going to break our problem into smaller problems in order to solve it. Let's get started. We have the following array and we want it sorted. We're going to continuously split the array in half, our divide step, until we are left with the individual items. Watch and see. Our array is now broken down into individual items. One note before we start sorting. When you implement this in code, these steps will be done in a different order because of recursion. But I think this human-friendly order provides more clarity in learning. Let's continue. We're ready to sort. We'll examine the individual items, compare their values, and merge them into temporary arrays. The temporary arrays are sorted, but there's work left to do. Let's jump up the recursion stack and continue. We merge our smaller arrays into a larger one, inserting items in the correct order. One more merge, and we'll have our sorted array. And that's it. Our array is now sorted. Here's the pseudocode for merge sort. On the left you have the recursive part, which halves the arrays. On the right is the merge function, which combines the arrays. Merge sort has a worst case time complexity of big O of n times log n. The easiest way to think about it is to start with the merge step. Looking at the while loop, we see we have to visit n items. The log n comes from the maximum height of a binary tree we create, which is on the order of log n. Thank you for watching. Please comment suggestions for future videos below.
Okay, so for the merge sort, in short, it will divide the array, and then while it divide the array into two partitions, it will sort each of the partitions. Okay, so after that, we will get all of the individual array, and then after that, it will merge again. So in order to merge it again, it will create temporary array. So this is where the disadvantages of the merge sort, because of because it needs a temporary array, so it makes the process is a little bit slower because of the temporary array. Okay, so this is what I meant just now. The one of the disadvantages of the merge sort is the use of the temporary array during the merge step. But the advantage of this merge sort is it is extremely efficient algorithm with respect to time, because the worst case of this merge sort is big O of n log n. So this is not the worst case, because if you remember all of the algorithm previously, it can reach the big O of n2 notation, n2 lah pula, n square. But this merge sort, it can reach up until big O of n log n only in all cases. So that's why it is effective in time. That's why it says the advantage of this merge sort is it is efficient, meaning it is faster. Okay, so this is the algorithm for the merge sort. This is it will require an array, and then it also will require the first value, the first element and the last element of that array. Okay, so after that, as long as the first element of that array is not it's smaller than the last array, then we can do this process. What is this process? Is we get the middle value, which is how to get the middle value is we get the first element and the last element, and then we divide by 2. After that, we do the recursive algorithm, which is merge sort. This meaning we call itself lah. Okay, so we do this recursive algorithm where it calling itself, and then in the first, but at the first it will take the first and the middle, and then after that we call it again, but this time it is passing this is the, if you see here, the first the first recursive call is it is taking the first half of the array because it is taking the first and the middle value. And then after that, the second process is it is processing the second half. I mean the second partition, because it divides it into two partitions, right? And then this is the process of it taking the first partition, and then this is the process of it is taking the second partition. So after that, merge the sorted half. Okay, so to merge it, use this formula. This method. Okay, so this method will use the array and then the temporary array and then first value and then the middle value, middle element, first element and the last element. So when you code letter, let's see if we have the code ready. This is let's see if we get the code ready in our example of sample code class. So bubbles. This is the bubble sort. Oh, so we don't have the example of the code, but this merge sort actually is implemented in our sort method for this from this library. It is already in the Java library lah. So this is if we open the array data, if you see, we find one method that called the sort. We check first sort array. Quicksort. This is all using edit. There's none using maybe here. Yes. Right. This is interface, of course. No. So, do you know that if you debug each of these, you can dig the functions when you do the debugging. For example, you want to see what happened, what is the code inside this, you can just no, not this example lah, better this one. Okay, for example, you want to know what happened in here, you can actually go and then debug it.
I tried before, but I still don't understand.
So actually, if you are curious what happened in this, you can debug lah. how to debug is you can just tick here in the line that you want to debug. Debug. And then later click F7. But okay. So let's say we want to see this object. What is the method inside this object? So we can just click here and then go debug. Oh, it didn't. For example, here, for debug. Wait, close others. Okay, so what I did just now, I go because I want to debug these files, and then I am curious what is this method doing, what is the code inside this method. Then what I did just now, I click this file, and then I right click, then debug file. Then it will stop in this line. So click F7 because we want to step into. So this is what happened. It is actually what the add method did is it will receive new entry. But we don't know what is the type of this variable at this stage. And then, so after we move to the next line, we know that this new entry is actually in type of integer. So this is new, this is actually in type of integer. So this is, when you click F7 again, then it will, I want to step it. So you can choose either step over, step into. Step into meaning you will see deeply in that method. But if you don't want to, if you want to skip some of the function or method, then you can just step over. It will go to the last line of that method. So you step over again. Okay, so the reason why we go to the Mac room just now because I click the F7 just now, which is the step into. And then proceed. I'm still step into, which is F7, but because this is not a method, then we didn't go anywhere lah. It's still there. So that is what happened in the end. Okay, so this is the use of step over, step into. Usually I will use step into or step over lah. Step over is if you want to go out from that method that you are currently in. So step into if you want to go in deeply into that method. Okay. So like I said, all of the exercises in this lecture now we will do next week because we still have next week to do the coding. Because why we didn't do it today? Because the material previously I received is corrupted and I don't have enough time to test each of the exercise. So that's why I won't just jump and then show it to you all. Okay, Kanuel, you understand ka? The
yeah.
debug. Okay, good lah. If this session have benefited you a little bit. Okay, so the code for this lesson for today, we will do next week, like I said, because I haven't have enough time to test the exercises. Okay, so this is okay. So we have learned about the bubble, selection, insertion, quick, and merge. Among these 5 algorithms, bubble, insert, select, suitable for small size of array, quick and merge is also suitable for the small size of array to the middle size of array lah. Okay, so after that, quick and merge is a recursive. Okay, so that is the summary that we have learned so far. So now we proceed to the selection of a suitable sorting method. So if you are wondering which sorting algorithm that you should use if you do the coding letter, so the factor that you need to consider is the speed. So remember the bubble is slowest, and then after that it is followed by insertion. After that it is followed by selection, and then the fastest is the quicksort. So that is the speed. Consistency of the performance among all of the sorting algorithm previously that we have learned. The most efficient is the merge, but it has the advantage lah, which is the creation of the temporary array. Okay, so memory requirement. Memory requirement among all of the algorithm, merge sort is the paling tidak berapa bagus because it require the temporary array, so it require more memory usage because of the temporary array. Okay, so the stability let me get back to you about this stability. I'm not sure what stability it means by each of the algorithm. And then the versatility of handling various data types. For this one, I think Quicksort is the best because it also can handle the data types that is not sorted in a natural way, because it can compare between two objects. Okay, so it is not only can sort elements or array that is that has a natural way of sorting lah. Like for example, I said previously, either it is increasing or decreasing or alphabetically. Okay, so Quicksort algorithm is the best because it can compare between two objects without regardless the natural way of sorting of that object. So the complexity of code and other programming language used. And then the nature of the data set. For the stability, complexity of code, and nature of the data set, I will get back to you both next week. Then
Okay.
Okay, so after that, this is the comparison of all except for radix and shell sort, because I think in this slide we didn't cover this. But I think this is more complicated lah. For you, that's why we only cover selection, all of this 1, 2, 3, 4, 5. 5 algorithm. So among all, if you see here, all of this, the worst case, they can achieve big O of n square, but only for the merge sort. It is consistent from the best case, average case, and worst case. It is big O of n log n. So if you see so we know that the worst case memang this one, big O of n square. So among all, we can see that merge sort is the most efficient algorithm because of this fact. So just ignore this too because we didn't cover it in this chapter. But if you see here, radix sort, we didn't learn this, but based on this, you know that we can know that because this O, big O of n is the like the best efficient, the most efficient. So we can conclude based on this figure, this based on this diagram, radix sort is the best lah. But because we didn't cover these two, so we only compare these 5 algorithm. So the most efficient one is the merge sort. But the fastest one is the quicksort. Because quicksort, comparing quicksort and merge sort, quicksort it also recursive, but it doesn't have the temporary array creation. That's why it is faster than merge sort. So this is what we have learned. We have learned about the sorting, selection, insertion, bubble. This one, shell and radix, we didn't cover lah. Okay, so because, and then we also assess the time efficiency of this algorithm. And then we know that from the big O notation, the best is the merge sort. Okay. So, like I said, we will cover the exercises on next week. We will see the code of each distort from the from the insertion until merge next week. Okay, so Noel and Kelvin, if you still don't understand, you can rewatch the video again. Okay, so after that, if you still don't understand, then you ask me next week. Okay,
Okay.
Kelvin and Noel. Okay. Kelvin? Okay, thank you. So we meet again on 2:30 this afternoon, and then we will continue to discuss practical 7, if I'm not mistaken. It is regarding Mr. Jafter lah. Okay,
Okay.
thank you.
Okay. Thank you.